Welcome back to Physics 141 online. I'd like to do an example problem involving a collision where we're asked to find something about the collision after, something about the objects moving after the collision, and also to figure out from our answer whether the collision is elastic or inelastic. And you'll remember that an elastic collision is one in which both momentum and kinetic energy are conserved. Inelastic collision, only momentum is conserved. Kinetic energy is not conserved. So I'll just make a little note of that, right? So inelastic, P only conserved. And of course we'll show how to do that using this particular problem. When you have an elastic collision, then it's the special case where both momentum and kinetic energy are conserved. So in this problem, we're not told ahead of time which kind of collision we have. We're going to use our answer to figure it out. And you'll notice that the common denominator here, both inelastic and elastic collisions, have the property that the total momentum is conserved. So first, let's read the problem and draw a sketch. A ball of mass m moving along the positive x direction with a speed v0 makes a head-on collision with a ball of mass 3m initially at rest. Alright, so that allows us to initially draw this ball of mass m with a speed v0 hitting an initial mass, or a mass 3m, that's initially at rest, just sitting there somewhere along the positive x-axis. Now, a head-on collision is a special kind where the centers of the two balls form a line, and that's the line along which the initial velocities of the two balls are moving. And as a result of that, it's going to be, when we have a head-on collision, it means that basically it's going to be a one-dimensional collision. The balls or objects will move along a single direction initially, and afterwards they will as well. And that's something that has to be true if momentum is going to be conserved. So later on we'll move on to more complicated cases where the collision is not head-on, but this is a simple one. So that's the before picture, okay? And then I'll just draw side by side what it looks like afterwards. And we're told that after the collision, the mass m that was initially moving in the positive x direction moves in the negative x direction now with half its initial speed, so v0 over 2, and we don't know what the mass 3m is doing. All right, and the question is, find its velocity in terms of the v0 that was given. So let me just say 3m, and I don't know for sure. I guess in this case it's pretty obvious that it has to move to the right, but in some problems we won't know that for sure. In any case, I'm just going to call its initial or its final velocity vf, and that's what we're trying to find. So since we don't know whether the collision is elastic or inelastic, the only thing we know for sure is that P is conserved, because there's no external forces acting on these two balls. They're only colliding with each other. Momentum, remember, is a vector, and so it's important that we indicate the direction, and we're going to call that, of course, the positive I hat, or the positive x direction for this problem. And that means that we apply the conservation of momentum. We add up the momentum of all of the objects in the problem before the collision, and then we set that equal to the momentum of all of the objects after the collision, pi after. And those have to be equal. Well, before the collision, it's easy because only one object is moving, and its momentum is mv0 in the I hat direction. So we're going to call it mv0 I hat. And that's important because it indicates that the momentum is a vector. The mass 3m is not moving, so it has no momentum. So afterwards, then, now we've got two objects moving, and the object with mass m is moving in the negative I hat direction, so its momentum is minus m v0 over 2 I hat. And I could have put the minus with the I hat, but it doesn't matter. And then, according to my picture, and I assume this is true, then it should have a momentum of, the mass 3m should have a momentum of 3m times Vf in the positive I hat direction. Okay? Now, Vf, I'm pretty sure that this mass 3m is moving to the right. It pretty much has to be if it's impacted by an object that's moving to the right. But if, let's say, I guess the wrong direction for this, then the only thing that would be different in my answer is I'd get a minus sign for it. So it doesn't matter which direction this unknown object is moving. I just pick a direction, draw the arrow in, and then make my equation consistent with that sketch. All right, so what we see here is that you've got two vectors on the right-hand side, and they both only have I hat components. And the vector on the left-hand side has an I hat component too. And so right away I can simplify this and say, well, this just means mv0 on the left is equal to minus mv0 over 2, right, plus 3m vf. And that's pretty obvious here. Now what I'll do is get all the v0 terms on the same side so that I can solve for vf. That's what I want to do, solve for vf. And so if I add mv0 over 2 to both sides, this equation gives me on the left-hand side 3mv0 over 2, right? Because I have mv0 over 2 plus mv0 plus mv0 over 2. And that gives me 3mv0 over 2. On the right-hand side, we're left with 3mvf. All right, the m term drops out because I can divide both sides by m. And so I'm left with, from this, 3vf equals 3 halves v0. And if I divide both sides by 3, I get the final answer that Vf is equal to V0 over 2. And the fact that the answer I got is positive means that it's in the direction that was drawn on the sketch. If for some reason I had gotten a minus answer for this, it would simply mean the magnitude's correct, but the direction is then opposite to what I chose when I set the problem up. Okay, so that's the correct speed. So we can say, right, that 3m moves with a velocity v0 over 2 in the I hat direction. That way it makes it clear that our answer tells us that it's moving in the positive direction. So the second part, we've done part A, so now part B asks us to determine whether or not the collision is elastic or inelastic. Well, elastic means kinetic energy is conserved as well. So what we need to do is just calculate the initial kinetic energy, calculate the final kinetic energy, and compare them. So the initial kinetic energy is 1/2 times the mass times the speed squared. So it's 1/2 m v0 squared. And since 3m is not moving, right, then it has no kinetic energy. So that's it for K initial. Now K final, we have two moving objects after the collision. Now, what's important here is that kinetic energy is always positive. It can never be negative. So it's not a vector. Momentum can be negative because it is a vector, but kinetic energy will never be negative. So when I write down the kinetic energy for the mass m, it's 1/2 m, right? And then it's moving with a speed v0 over 2, and so I just square that. So be careful here. That's going to be now the kinetic energy of mass m. Now mass 3m has a kinetic energy, so it's plus 1/2. Now be careful here. The mass is 3m, so it's 1/2 the mass times the speed, v final squared, and we know that v final is v0 over 2. Right? So it's v0 over 2 squared. And let's simplify this expression for the final kinetic energy. So 1/2 times, and then what I have inside the parentheses is a 1/2 squared, which gives me a 1/4. So this gives 1/8 m v0 squared, the first term is. The second term, well, I've got 3/2 m, right, and then the v0 over 2 squared gives v0 squared over 4, which then, if I simplify again, I have 1/8 mv0 squared. This second term is 3/8 mv0 squared. I'll write it out just to be very clear. 3/8 m v0 squared. 1/8 plus 3/8 is 4/8, which is the same as 1/2. So I get 1/2 mv0 squared as my final kinetic energy. And if I compare that to the initial kinetic energy, I see that in this case, both are the same. And so the collision is elastic. I can tell that simply by calculating the kinetic energies. So, unless I'm told otherwise, I can't assume that a collision is elastic, but by solving in this case for the final speed of the mass 3m, it was easy to then calculate the initial and the final kinetic energies and compare them. So it's a relatively simple problem. We use conservation of momentum to find the missing piece of information, and then, based on that, we can calculate kinetic energies. Now, collisions like this won't always be elastic. In fact, elastic collisions are kind of the exception. But this was a case where the final velocity that was given for the mass m was consistent with an elastic collision. So I'll be doing some other examples of collisions like this where we might be told up front that the collision is elastic and then use that information to help solve the problem. I'll see you in class.